All right, McMurray 16.9, reduction of aromatic compounds. Okay, so 16.9. We're going to reduce aromatic compounds. We're going to reduce these aromatic rings. Well, first let's establish that they're different again. If we take this alpha-beta unsaturated carbonyl that has a phenyl group at the para position, if I remember correctly, that's chalcone, under sort of the standard heterogeneous catalyst conditions, which would be H2 at 1 atmosphere, with palladium on carbon and something like ethanol as a solvent. Alcoholic solvents are good for hydrogenations because hydrogen is very soluble in alcohols. We get reduction of this double bond, and the product retains the aromatic ring. And it takes much higher temperatures and reaction conditions and much more active catalysts. So for instance, a couple of catalysts that will work to reduce the benzene ring. We can use platinum metal with hydrogen, again in ethanol, but we will have 130 atmospheres of hydrogen, and we can do that with that much pressure at room temperature. And the product that we get, of course, once we break the aromatic ring, the other double bonds very quickly are reduced. So if we take away one double bond, that would leave a diene. A diene is not aromatic, and of course that rapidly goes to full reduction. So the benzene ring absorbs 3 moles of hydrogen, and notice that we get the cis product. Okay? Another catalyst system that is very effective for these is use of rhodium metal, but it's problematic because rhodium makes gold look cheap. So if we take this para-T-butylphenol, we use rhodium on carbon. Now what does that mean, rhodium on carbon? Well, I just said rhodium was really expensive. And imagine we had a little sphere and it was solid rhodium. Only the rhodium right on the surface is active. So what we do is we take carbon spheres and we distribute the rhodium on them. Okay? So that internal portion, kind of like the Earth's mantle, is carbon and it's unreactive, and so we can not waste that expensive rhodium catalyst. If we do this with H2 at 25 degrees C in 1 atmosphere, rhodium will actually catalyze this hydrogenation, and again we get the cis product in these systems. And I won't get into all the details about the mechanism of this reaction. That's beyond the scope of our present course. All right, so that's the reduction of the aromatic ring itself. Now again, we've seen that that benzylic position, which is next to the ring, is very different and it's very important. So for instance, imagine if we needed this isopropyl, and in fact with that carbon isobutyl group in something like ibuprofen. Ibuprofen has an isobutyl group in it. That's where the part of the name for ibuprofen comes from. If we react these benzylic carbonyls, particularly ketones, with hydrogen and palladium on carbon, typically it's with an ethanol or methanol solvent, it actually will reduce that benzylic carbonyl all the way to a CH2 group. Okay, so it's a complete reduction. And that's very useful, right? Because we can't put this isobutyl group on using Friedel-Crafts alkylation because of the rearrangement problems that occur. But with Friedel-Crafts acylation, we can get selective and good yields of this by Friedel-Crafts acylation. Go back and look that up and write out the substrate if you need to see that. Friedel-Crafts acylation would give us this with benzylic reduction conditions. We can produce the CH2 and we can get that isobutyl group, which again is what's present in ibuprofen. All right, so if we put all of this together now, we need to be concerned about cross-reactivity. And there's a nice little example that is given in your textbook. The nitro group, turns out, is very easy to reduce. And so if we wanted to reduce that carbonyl with these conditions, palladium on carbon and hydrogen, just remember this group is very easily reduced and it will reduce also. To the NH2 group. Now, in synthesis, one of the key things that we need to be able to provide is selectivity. That is, to reduce this without reducing that. Palladium on carbon does not provide that. And in a later chapter, when we learn the chemistry of carbonyls, we'll learn about the Wolff-Kishner reduction, which is what I'll call a mechanism-based reduction that will allow us to achieve that selectivity. Selectivity is one of the key things we want to produce for organic chemistry.